Let us have a look at the manufacturing section of the final exam of 2012. Question 1.1 says, which one of the following is not a machining operation? So remember, machining is when we specifically cut away material or remove material in very specific locations to yield a final part shape that we desire. So basically any cutting process would fall under machining. So number 8, drilling. Drilling is when you use a spiral cutting tool to cut a circular hole into a component. So it is definitely not drilling because this is a machining operation. Broaching is a cutting operation where a cutting tool is moved across a surface to cut a desired shape into the surface, so not broaching because it's also a machining operation. Grinding is abrasion on a surface to shape the surface by removing small particles of material, so that's also a machining operation. Drawing is when you take a material and under very high pressures you shape it into a different cross-sectional shape. So drawing is not a machining operation. And high energy beam machining, as the term says, it is a machining operation. So the only one that is not a machining operation is 1.1D, drawing. Number 1.2. The most widely used casting process is A. Sand casting, die casting, lost wax casting, slush casting, or expanded polystyrene process. So the most widely used casting process is actually A. Sand casting. That one comes straight from the theory. So next we have this weird little dustbin. It's got an outside size of 200 diameter, height of 250, and from the side it's got this bean-shaped handle that's cut in, and you can see it from the right hand side as well. So question 1.3 says, you are working at a sheet metal factory and you have been tasked to do the design of a dustbin as depicted in figure 1.1. Calculate the starting blank size for this dustbin to be used in a drawing operation. So we want the starting blank size for the dustbin in a drawing operation, and you may ignore bend radii. So usually when we say that, we refer to this little radius at the bottom corners. Right, so basically in a drawing operation, remember we are reshaping the material, but we're not adding or subtracting material. So basically that means the volume of the final product must equal the volume of the starting blank. Now with this dustbin, we will first do a drawing operation and then we'll cut the holes out of the handle. That's why question 1.5 actually says, which we haven't done yet, calculate the force for cutting the handle out. So basically the starting blank is this starting volume of the cup without the removal of the two handle holes. And that must be equal to the volume of the flat disc that we use to make this component of. So that means the volume of the cup must equal the volume of the blank. So, volume of the cup, easiest way to calculate that is to go and work out the outside volume of this cylinder and subtract the volume on the inside from that. So the volume of the cup is, you can use pi r squared times h, or you can use pi over 4 d squared times h. It is the same thing. And from that we are going to subtract the inside volume, good. So the volume of the cup is pi over 4. Outside diameter was given as 200 millimeters. Remember, we want to always use meters or SI units, so that will be 0.2 meters squared times the overall height, which is 250 millimeters. Or 0.25 meters. Minus pi over 4. Now we need to determine the inside diameter. So from the question, the outside was given as 200 and the thickness is given as 2 millimeters. So on the side and on the bottom it is 2 millimeters thick. That means the inside diameter is 200 minus 2 minus 2. So minus 2 on each side. So that's 0.2 meters minus 2 times so 0.2 minus 2 times 10 to the minus 3, so this is 2 millimeters converted to meters times 2 because it's 1 on each side, and then the 0.2 meters is just the original outside diameter squared, and the overall outside height was given as 0.25. So the inside height is 0.25, and from that we subtract two millimeters. Okay, so it's pi over 4 outside diameter squared times outside height minus pi over 4 inside diameter squared times inside height. This will give us the volume of the material used to make that cup shape. That gives us an answer of 0.371 times 10 to the minus 3 cubic meters. And this must be equal to the blank volume. So the blank is basically the volume of the flat disk that was used to make this component The thickness stayed the same. It was given as 2 millimeters. And we now need to determine this diameter. So the volume is pi over 4 dB for blank diameter squared times the thickness t, which is equal to pi over 4 dB squared 2 times 10 to the minus 3. So now if we set the blank volume equal to the volume of the cup, then we can solve for dB. So if you do that, you get dB equal to 0.486 meters. So that is the blank diameter. Let's have a look at the options given. 0.486, 0.7, 0.528, 0.443, 0.379. So 1.3, correct answer was A. Question 1.4. This question asks, would this drawing operation be feasible in one single drawing step? So for that we need to go to our ratio of the blank diameter to the punch diameter. You'll remember there were those criteria which said dB over dP should be less than 2 for it to be feasible in a single drawing step. So this is 0.486 and the punch diameter was 0.196, and this answer would be bigger than 2. 0.486 is more than twice 0.196. So that means this drawing operation would not be feasible in a single drawing step. It can be done in more than one step. So, question 1.5. Calculate the force required to at once punch out the handle hole in the dustbin in figure 1.1 if the effect of the 200 mm diameter curvature is not taken into account and the material used has a shear strength of 400 MPa. Shear strength is 400 times 10 to the 6 pascals. So if we go back to the question, I'm just going to bring that up again. Over here we are given the dimensions for this hole, for the handle part. So it has an inside radius of 50, the bigger radius is 100, and on the ends we have two radii of 25, and we're given 60-degree or 1/6 rotation over there. So let's have a look how to calculate that. In a cutting operation, force is equal to STL. S we're given 400, T is the thickness, that was 2 in the question. L is the length of the cut, which is what we need to determine first. So we're given that this shape is 1/6 of a rotation. This radius is 100. That radius was 50. And at the end we had a R25 this side and a R25 on that side. So the length of the cut is basically this outside perimeter of the handle shape. So let's calculate the arc lengths individually. Arc length for, let's call this number 1. For number 1, the length is, how will we calculate this? This is a radius 100 and we are given that it is 1/6 of a circle. So we can calculate the circumference of a complete circle and then divide that by 6. So circumference of a circle is 2 pi r. And we then divide that by 6. You could have also used pi times diameter and just divided that by 6. So that gives you more or less 104.72 millimeters. L2 is this half circle on this side and the half circle on the other side. So together these two halves make a complete circle. So length 2 is this side and that side added together, so it is 2 times this arc length, which is 2 pi r, times 25. And then length 3 is this 6th rotation of a circle with a radius of 50. It's 2 pi 50 over 6. That gives me a total length of 100 divided by 6. So it's 100 pi over 6. Just for interest, the first one was 200 pi over 6. You could have left it in pi form as well if you really wanted to. So L total is then equal to 50 pi. That would be for L2, 2 times 25 pi, plus 200 pi over 6, plus 100 pi over 6, gives us an answer of 100 pi. Now we can use that 100 pi in my F is equal to STL equation to calculate the force. So F is equal to STL, which is equal to 400 times 10 to the 6 times 2 times 10 to the minus 3 times 100 pi. Remember, this answer was in millimeters, so we must just divide this by 1000 to get it to meters. So that, if you work that out, gives you an answer of 251.33 kilonewton. Let's see if we have any of those available. A 126, B 251, C 98, D 318, E 223. So 1.5, correct answer is B. Question 1.6. This one says a true centrifugal casting operation is to be performed in a horizontal configuration to make cast iron pipe sections. The sections will have a length of 3 meters, outside diameter of 1 meter, and a thickness of 20 millimeters. Determine the G factor for a rotational speed of 300 revolutions per minute. Now remember, the outside diameter of the pipe was given as 1 meter. Now, the outside of the pipe is equal to the inside of the mold. Remember, this thing now goes into a spinning mold. As the mold spins, the molten material is poured in, it spreads around the circumference and solidifies to give you the pipe at the end. So, the outside diameter of the pipe is equal to the inside diameter of the mold, meaning this 1 meter is the value that we are going to use. G factor needs to be determined for a rotational speed of 300 revolutions per minute. So N is equal to 300. And from the formula sheet, there was an equation N is equal to 30 over pi This equation is relating the rotational speed to the G factor as a function of the diameter. Remember all of the units here? Meters per second squared, G factor doesn't have a unit, and there we have meters to work with the meters per second squared at the top. So this D must be given in meters. So 300 is equal to 30 over pi square root of 2 times 9.81 times G factor divided by the diameter was given as 1. So this G factor works out to 50.3, which is option E. Now the problem is, one thing to just remember with centrifugal casting, G factor must be between 70 and 80 or 60 and 80. So 50.3, although this is the answer to the problem, just remember that it would probably not be sufficient to successfully cast this pipe. But the answer was E50. Question 1.7. Which of the following is a disadvantage of die casting? Remember, die casting was the process where you have metal molds and the molten material is injected under high pressure between the molds. So these two molds come together, material is injected, and then the molds split apart again. So something to remember with this splitting apart of the molds, it has to be such that you cannot have any hugging around of the mold. If it hugs around the part, you won't be able to split the mold again. So your shape is a problem in die casting. You can't have very complicated shapes. So which of the following is a disadvantage of die casting? Shape restriction is a disadvantage. High production rate is an advantage, not a disadvantage. Quick cooling time is also a material advantage or process advantage for material strength. Thin components, this is also an advantage, not a disadvantage. And surface finish depends on the mold surface, so it can do pretty much any surface finish you need. So the correct answer here is 1.7a. Shape restriction is the problem with die casting. Question 1.8. I'm just going to zoom out a little bit. Question 1.8 says a sheet metal plate 50 millimeters wide is to be bent as shown. Okay, so it's 50 wide, this length is 40, that side is 40. Inside radius is 5, thickness is 4, and the angle through which it is bent is 45 degrees. Determine the starting length of the sheet metal plate before bending. So we basically need to calculate the bend allowance for this curved part. And then once we've calculated the bend allowance or the arc length of the bent part, then we can just add the two straight parts. Okay, pretty easy. Inside radius is given as 5 millimeters. The angle through which the plate is bent is 45 degrees. Plate thickness is 4 millimeters. So, bend allowance is equal to 2 pi a over 360 multiplied by inside radius plus kPa times t. So, kPa we need to find based on the ratio of the radius to the thickness. So kPa So kPa is 0.33 if r is less than 2t, and it is equal to 0.5 if r is bigger than 2t. So thickness is 4, 2 times the thickness is 8. So my radius is less than 2 times the thickness. So I'm going to use the 0.33. Now let's plug everything into the equation. Bend allowance is 2 pi 45 over 360 times 5 plus 0.33 times 4, and if you work all of that out, you should get 4,964 millimeters. So that is the arc length over there. So now my total length is my bend allowance plus the two straight portions of 40 millimeters each, .964 millimeters. Let's see which answers we have. 81.96, 84.96, 86.56, 88, 87. So the correct answer is B. So next we are at the machining or turning and milling questions. So first let's have a look at this component. It has an initial diameter of 40. Then this front portion of the shaft is cut down to 30 millimeters in diameter. And after that, a flat portion is machined in using an 18-tooth milling cutter. Now remember, this cutter, if we view it from the top, if the cutter's feed direction was in an axial direction, then the cutter would actually cut an arc over there. So that means the feed direction cannot be axial. That means the feed direction has to be radial, like that. So the cutter comes in from this opposite side and moves over the surface until it exits on this side. So now that we have a good idea what's going on, now we can do question 1.9. So question 1.9 says, a round bar is to be machined to yield the part in figure 2. Okay, we have just looked at that. The part's diameter is reduced in a lathe, after which a flat portion is cut on a milling machine. Given a cutting speed of 80 meters per minute, calculate the feed required to perform the cut from a diameter of 40 millimeters to 30 millimeters in a time of 1 minute with a single pass. So cutting speed, that's my velocity, equal to 80 meters per minute. We want to calculate the feed. That's just a small f. Feed is unknown. Initial diameter is 40, final diameter 30. So initial was 40, final is 30. So that means the depth of the cut small d, is equal to 40 minus 30, which is 10, divided by 2, equal to 5 millimeters. Okay, good. Now we can try to calculate the feed. So, and we're given time is 1 minute. So from our formula sheet, time is equal to the distance we traveled divided by the speed at which we were traveling. Time is L over FR. Now the length of the part that is cut from 40 to 30 is this entire end of the shaft, reduced from 40 to 30. So the length L is 60 millimeters. Thus we have 1 minute is equal to 60 over feed rate. That means my feed rate is then equal to 60 millimeters per minute. That was pretty straightforward. We're looking for the small f. We have Fr, and there's an equation that says Fr is equal to rotational speed times my feed. So 60 millimeters per minute is equal to rotational speed n times f. Now the n we need to determine from the original diameter of 40 and the surface or cutting speed of 80 meters per minute. So n is equal to v over pi d. So that's 80 over pi times 40. Now there's a mistake here. This is meters per minute. This is millimeters. So I'm just going to multiply by 1000 at the top to get it to millimeters and millimeters. So then we can calculate F from this equation, and we get F equal to 0.094 millimeters per revolution. So if we look at the answers available, 0.1, 0.094, 0.078, 0.113 and 0.106. So the correct answer is B. Then the last question, question 1.10, says a face milling operation is used to machine the top off of the cylinder with the cutter as given in figure 2. Calculate the time it will take for the cut to be completed given the following. A chip load of 0.1 millimeters per tooth and a rotational speed of 500 revolutions per minute. So chip load, that is the small f in a milling operation. Rotational speed of the cutter is 500 revolutions per minute. That's equal to n. And we need to calculate the time. Time is unknown. I'm just going to go back to the picture given. We're given an 18 tooth. That's small n t for number of teeth. And it's got a 50 millimeter diameter. So that means big D is equal to 50. The shaft we are machining has a width of 30 millimeters. We're machining at the end where it has a diameter of 30. So let's draw a picture of what's actually happening over here. There it's got a diameter of 40. At the end it has a diameter of 30. That length is 20, this length is 40. My cutter has a diameter of 50, which is slightly bigger than this gap. Diameter 50. So as this cutter approaches the work part, the first point of contact will be somewhere there, 10 millimeters, or what's it, 15 millimeters from the bottom. Because this radius is 25, that is 40, so that would be 15 from the bottom. First point of contact is on the outside edge over there. So as it starts to make contact, we'll have an approach distance . And the approach distance is half of the diameter of the cutter. Because we're not making contact somewhere on the edge over there, we're making a contact on the furthest point from the center. So that means my approach distance A is equal to 25 millimeters. Now the question said it is a face milling operation, so after we are done cutting to this point, we actually need to over travel the work part as well. I'm just putting the quotation marks there that you know it's a O and not a 0. So this side we have our approach distance, there we have our over travel distance. And it is over travel because it is a face milling operation. Basically what's happening as this cutter is rotating, it cuts mainly with the side of the teeth, but the bottom of the teeth still make contact with the surface. And if we just cut until the center is over the edge, if we lift up, then we're gonna have a discontinuity in the pattern left on the surface. So with face milling you have to always over travel until the component doesn't make contact at all. Good. So we are given n and small f, so we can calculate our feed rate. Feed rate is n times nt times f, so that is 500, times the number of teeth, which was given as 18, times 0.1. So that means the feed rate, basically the speed at which this cutter is moving through the work part, is 900 millimeters per minute. So now that we've calculated the feed rate and we know that we have an approach distance, the width of the work part, and an over travel distance, we can find the total length of travel as 25 plus 30 plus 25. Which is equal to 80 millimeters. $25, $55, $80. So now the time equation is the total length we have to travel divided by the feed rate, which is then 80 divided by 900, which gives us 0.089. This was millimeters, this was millimeters per minute. So this answer is then 0.089 minutes. To get it to seconds, because all of our options given in the question are in seconds, we have to multiply it by 60. So if we multiply that by 60, we get an answer of 5.3 seconds. If we look at the options available, option A 3.8, not that one, option B 12, no, C 5.3, 21, 9. So, correct answer is C, 5.3 seconds. So that's it for the manufacturing part of the 2012 exam paper. I hope this lesson was insightful.